Hello, everyone. This is Swagat from Center for Theoretical Physics of the Universe from DESI, and I am absolutely delighted to be talking at Dark Energy from Home 2026. So we now have a standard framework of cosmology, which is general relativity and flat lambda CDM. And this framework is based on two sets of assumptions. The first set of assumptions is about the composition of the universe, that apart from standard model of particle physics constituents, universe has whole dark matter and dark energy as a cosmological constant. And also combined with these assumptions, once we have spatial homogeneity and spatial flatness and presence of initial fluctuations of specific type, we can actually explain the evolution of the universe starting from about 1 second all the way to 13.8 billion years very, very well. So this is a remarkably successful framework that we have. And since this conference is about dark energy, let's focus on lambda in lambda CDM model. So it's a cosmological constant. So its density is constant. It also has a constant negative pressure. So the Hubble parameter in such a system tends towards a constant asymptotically into the future. So this is a classical de Sitter space in that sense. And acceleration of the universe also tends to the same positive constant. So we have an eternally accelerating universe into the future. And in such a universe, structure formation freezes asymptotically. And that's the future of the universe. And this is a very nice toy model for dark energy. However, it has conceptual issues. In particular, the observed value of cosmological constant might get two kinds of contributions. One is from the classical cosmological constant in general relativity, and the other comes from vacuum fluctuations of quantum fields in the universe. So the observed density is actually a combination of the classical part and the quantum part, both. And what we observe is this combination is much smaller than the Planck scale, more than 120 orders. In fact, it's even smaller than about 70 orders smaller than the Large Hadron Collider scale, which is at least should be the contribution from the quantum part. So there's some kind of cancellation going on. So this is an extreme fine tuning. Well, apart from fine tuning problem, universe becomes dark energy dominated towards the present epoch after structure formation has taken place. So it's a coincidence problem. Cosmological constant also has a radiative correction problem, which is the most difficult problem to solve. But if there is some mechanism because of which the total cosmological constant is zero, then maybe dark energy could be some dynamical component which may not have fine tuning or coincidence issues. So people have started looking for dynamical dark energy beginning from the discovery of acceleration of the universe in late 1990s. So whatever dark energy is, it is some new physics for us. And that's why in this conference, we are talking about dark energy. So what is the current observational status of dark energy? It is kind of a gold standard of observational cosmology in the context of dark energy is to combine different set of observations to break degeneracies and to have precision measurement of cosmological parameters. To give an example, if we combine CMB and BAO and type 1a supernova, then we can, for example, in lambda CDM, we can break omega lambda and omega matter degeneracy. So this was kind of expected 2.5 decades ago. And now we think that this combined parameter space has shrunk at least 10 times more since then. So this is what we want to achieve in this particular decade. And the experiment which is relevant to my talk is dark energy spectroscopic instrument, DESI. We will have a lot of talks in this conference about DESI. So I'll just briefly mention that this is a galaxy clustering, particularly BAO observation. And it's a stage 4 cosmological mission, which spectroscopically studies about 14 million galaxies or so. And it's a proud successor of SDSS and BOSS. And it has had two sets of data releases, data 1 and data 2, 24 and 2025. It's located in Kitwick Observatory in Arizona. Okay, so if I have to state the observational results very briefly, then lambda CDM works pretty well given the DESI data. However, if we compute omega matter and Hubble from DESI, it turns out to be in tension with the latest CMB observations. The tension varies in between 2 to 3 sigma, and we'll hear updates about it in this conference. So there is some tension. That kind of motivates us that probably dark energy is not cosmological constant, maybe it is something else. Just a quick comment that if we include curvature instead of flat lambda CDM model, this tension is not alleviated. The curvature is not the reason. So perhaps it is dark energy being something else. In particular, let's say dark energy is dynamical. So it has an equation of state which is not -1. So it is evolving with time. If we know the shape of equation of state as a function of redshift, we can compute Hubble. I just use this fraction of dark energy, FDE. FDE is basically dark energy density at any redshift as compared to its present value. It can be known by integrating the equation of state. Okay, so that will be important parameter. Other parameters which may be important is this ohm parameter. This is a null test for lambda CDM. It's an ingenious way of defining this parameter in terms of background quantities so that it is equals to omega matter only in lambda CDM. If there's a departure from lambda CDM, then it will not be omega matter. And since we're talking about acceleration of the universe, so of course, we are interested in the plotting the deceleration parameter. The simplest form of dark energy, which is not lambda CDM, whose density is changing, could be a constant equation of state, which is not equals to -1, but that doesn't alleviate this tension. So we'll directly talk about dark energy whose equation of state is evolving. In particular, the CPL parameterization, which is very popular, which has two extra parameters, W0 and WA. And you can see that since this is a closed form, it's very easy to integrate this and compute Hubble as a function of redshift in this parameterization. It is actually quite generic. Here is equation of state as a function of redshift. And if by varying W0 WA, you can cover a large range of space here. Just to remember that today at redshift 0, equation of state is W0, while in the very past at high redshift, equation of state is W0 plus WA. Since universe is matter dominated, this combination has to be less than 1. So it's kind of a prior for this model. What happens if we fit this model to DESI data? It turns out it fits the data better than lambda CDM. How significantly better depends on the combination of data set, and it's also changing from analysis to analysis. I will state the original things which were quoted in DESI DR2 data release. So here is WA and here is W0. WA is 0 and W0 is -1 is lambda CDM, which sits there. What is plotted here is a combination of DESI and CMB and some supernovae, Pantheon Plus or Union 3 or Dark Energy Survey 5. And that kind of covers a contour here, which excludes lambda CDM at 2 sigma level. The exact value depends on the exact parameter. So it lies somewhere between 2.8 to 4.2 sigma as per the original update. What would we infer from it? If CPL is dark energy, given DESI data, then the equation of dark energy seems to be evolving quite strongly at the present epoch. And in fact, in the past, the equation state seems to be less than -1. It's called phantom-like. So it was less than -1, and then it becomes greater than -1 towards present. So the density of dark energy seems to be growing in the past, reaching a maximum around redshift 0.5 or so, and then beginning to decay away. So that's the trend. And this trend is not only just a feature of CPL, but many different parameterizations also display this kind of trend. Also, non-parametric reconstruction of equation of state of dark energy and other cosmological parameters would also indicate similar trend. So we have some reason to believe that probably this is an evidence of dynamical dark energy. So if you have to summarize the inferences, is that does it mean it's a fall of lambda and do we have phantom? So particularly we saw the following, that DESI combined with CMB and supernovae seems to be indicating that dark energy is dynamical and it is decaying away at low redshift. It was phantom-like at redshift greater than 0.5 roughly. So its equation of state was less than -1 and density was growing. And today it is quintessence-like, so its density is decaying today. So somewhere around redshift 0.5 or so, it crossed this phantom divide. So it went from less than -1 to greater than -1. Now, in general, phantom substance in field theory is a pathological substance. It violates the null energy condition, and it would have negative energy states. So it's inherently unstable. It has vacuum instability. So it's pathological. Also, if such a substance comes and dominates the energy budget of the universe, then we will have a big rip singularity into the future. Well, that turns out not to be the case for DESI because dark energy starts to decay away eventually. Question is, if we have to explain DESI observations by modeling dark energy, how can we obtain phantom dark energy without leading to any internal instabilities in the system? So that brings me to how to construct dynamical dark energy in light of DESI observations. So how can we obtain dark energy which is effectively phantom but not inherently phantom? This can be done in many ways. And in fact, since the announcement of DESI data, there has been a major effort to try and construct this kind of scenarios, sensible models. So one could be dark matter dark energy interaction. The other could be non-minimally coupled dark energy. And the third one, which I am going to talk about in this talk, is modification of general relativity, being the reason for such kind of phantom-like behavior. Okay. The specific model that I'm going to talk about is an IR modification of gravity due to the presence of a single extra dimension. And such models are called Braneworld models of dark energy. And these, the particular Braneworld model that I am talking about is called the ghost-free Braneworld, sometimes called normal branch of DZP, whose cosmology was pioneered by Sani and Stanov in the early 2000s. The scenario is actually quite simple. Our universe is considered to be a 3+1 dimensional brane, which is embedded in a higher dimensional bulk, one extra spatial dimension, so 4+1 dimensional hyperspace. And this extra spatial dimension is nothing fancy. It's not even compact. It's a large extra dimension, which is flat, basically. Okay. So this picture is kind of this Braneworld model. All matter fields are constrained to be on this 3+1 dimensional brane or our universe, while gravity is free to propagate both in the brane and in the bulk. The action for such a system is very, very simple. The action has a bulk gravity term, Einstein's gravity, has a brane gravity term, Einstein gravity, and a matter term. And the matter term is basically all matter, dark energy, variance, everything. The extra dimension has a Planck constant or G, and brane has a G, and their ratio could be taken to define a length scale, a characteristic length scale. This length scale basically indicates that what is the length scale over which you see the effect of extra dimension as modification of gravity on the brane. Okay. So if the length is large, then you will not see it even at cosmological scales. If the length is small, then you would see it at small scales. Okay. So, and we can convert this length scale into omega by just using Hubble parameter, a dimensionless omega. Now let us consider such a Braneworld model in which our universe is a Braneworld with a brane tension, which is not zero. So universe has a cosmological constant, basically. Now the modification of gravity on the brane because of the presence of extra dimension actually induces an extra term here. So otherwise you have the same Friedmann equation as before, but just an extra term here. From there, we can compute Hubble. We can determine Hubble, and it turns out to be the familiar expression with omega L added and then subtracted out. Okay. If omega L goes to 0 or length scale goes to infinity, that is GR, and then otherwise we have modification of gravity. In such a model, if we compute the effective dark energy density, which is just total Hubble minus whatever is the matter part, the dark energy density takes this particular form. And notice that at early times when universe is matter dominated, Hubble is falling while cosmological constant or brane tension is constant. So effective dark energy density is actually growing. So dark energy is phantom-like at early times, which is important. But now I have demonstrated you that you have phantom-like dark energy without any phantom matter, which is put into the Lagrangian. So this is an effective phantom, which I was talking about. And the original authors highlighted this long back. Okay, that's great. At late times, as matter density falls off, both the terms become constant. So dark energy density becomes constant. So you go from phantom towards a cosmological constant at late times. However, that does not lead to phantom divide crossing. So it is not able to explain DESI data. To explain DESI data, then we thought maybe there is no brane tension, but there is a scalar field on the brane. In particular, thawing scalar fields which can decay. And so this is our work, which we try to explain with DESI data, which is published in JCAP. If you're interested, please read. Let me explain. We have thawing scalar fields, which is initially frozen due to Hubble friction. And as time progresses, the scalar field kind of gets released from its position and then evolves away or decays away. Either it oscillates at late times or decays away forever, depends on the type of the potential. So that's basically very simple. So we have a Braneworld and a scalar field on the brain. Now we have the similar equation as before I showed you, but just that instead of a brain tension or a constant, now we have a scalar field density sitting there. So in such a setup, if I determine dark energy density, effective dark energy density, it's now that Hubble which was there previously, but a scalar field term which might evolve. At early times, the scalar field is frozen by Hubble friction, and Hubble is decreasing because universe is matter dominated. So dark energy density is growing. So we have phantom-like behavior at early times. At late times, once the Hubble friction becomes negligible, the scalar field starts to get released from its position and evolves. And if it evolves fast enough, then the total density can fall as a function of redshift as we come to low redshift. So we can cross the phantom divide. That was our original motivation to look at into this model. Of course, for this model, we can plot anything. Distillation parameter, fraction of dark energy, ohm. Let me just show you that the equation of state, if we compute a little bit in this model, it becomes this simple form. -1 plus a kinetic term minus omega matter. At early times, the scalar field is frozen. So the kinetic term is 0. So it's phantom-like. At late times, the kinetic term may become significant. So then it's -1. If the kinetic term is higher than that, then -1 plus, which gives us quintessence-like or decaying dark energy. And here's a trend that we kind of computed in this model analytically. If I just stick to a simple m square phi square potential, just one extra parameter m, and the trend of equation of state is like phantom-like in the past and crossing and becoming quintessence-like is very similar to DESI. The fraction of dark energy again grows in the past and then decays away. So we then went seriously to test it against the data. This was performed in Kasi cluster, Kobaya. And the data combination is very similar to what DESI used. So we used Union 3 and CMP compressed data set and DESI DR2. Here's the best fit value of the equation of state from different potentials, which are different color. And this black line is basically CPL fitting DESI. And you can see that at late times, the behavior is very similar. Our equation of state is very similar to CPL. So it explains DESI data very well. At early times, though, the curvature of our equation of state is different. So that's some kind of a distinct signal in our model. Now, quantitatively, here's the parameter estimation. These are our different models, and these are different cosmological parameters. You just look at chi-square. This chi-square is determined with respect to CPL. So how good it fits DESI data with respect to CPL, and you can see it's almost 0. So which means it fits DESI data at least as good as CPL. So it fits extremely well. We also understand why all of our different potentials kind of lead to the same best fit value, because the data kind of forces the different potentials to have at late time similar value of phi and derivative of the potential. So we also understand why all potentials fit equally well. So then the simple m square phi square is pretty good so far. Best fit value of the Braneworld parameter is roughly 0.013, and that turns out to be very, very consistent with any previous constraints coming from perihelion precision of solar system planets, basically. So omega 0L should be less than 180, and ours is 0.01. So very consistent. And so that was another surprise. So such a simple model fits the data very, very well without violating any of the constraint, and also has some specific features which is different from the standard CPL. So let me conclude here that there is evidence for evolving dark energy with some surprising properties, that dark energy is phantom at early times and quintessence-like at late times. So if this is not systematics, then probably this is coming from some physics. This physics could be of two types. One would be that the Friedmann equation is probably different, so modification of gravity. Or it could be that dark matter and dark energy are not evolving freely as ideal fluids, but they have some interacting fluids that could cause it. So whichever is the case is of course to be seen in the upcoming data set. So there are different types of models. In our model, we are now computing perturbations in this Braneworld to see the growth of perturbations so that to see if they obviously violate something or they predict something, some interesting feature. The other thing is the curvature of our equation of state is different, so it requires some kind of test beyond CDM, which actually we are working on now.